Martin, thank you very much for accepting the invitation to be here with us. It's a pleasure to have you here. And I'm sure that the audience will love to hear about gravitational waves and all the whole world that is opening up to us through this work that you guys are doing. Thank you for joining us. And the floor is yours.
Thank you very much, Rosa. I'm really delighted to be part of this wonderful event. It has been a very strange few months. As you know only too well, I travel a lot, or at least I used to. And of course, the other place where we met last year was in the island of Principe, which was a fantastic experience to be part of the 100th anniversary of the eclipse observations. And I'm still very much in eclipse mood because 3 years ago, yesterday, was the grand eclipse in the US, which was referred to in earlier presentations. And I was enthralled to see that total eclipse for myself. But in fact, on August 21st, 2017, I would contend that that was only the second most interesting astronomical event which took place that week. And what I'm here to do this evening is to share with you some of the excitement and the science that we learned from, in my view, the most exciting astronomical event of that week in 2017. But it's not just about the past. I also want to share with you what's coming next in the world of gravitational wave astronomy. So let me share my screen, and before I say too much more, we can just check that it is visible to everyone. Okay, there you go. So you should be seeing my title slide, and hopefully Perfect. You can hear me. And I'm so sorry, I forgot the important thing I need to do is to make sure that I share my sound. So let me do that just one more time, and this time with sound. Because I've entitled this talk, Listening to Einstein's Universe, and as I will explain a little later, sound is a useful metaphor in understanding the nature of gravitational waves. Gravitational waves are not sound waves, but we can use our intuition about sound and about noise to help us understand how we detect these gravitational waves. So my talk is going to be sharing with you a lot of the outreach that we have done to tell the world about our gravitational wave detections. So I chair the Communications and Education Division for the LIGO Scientific Collaboration. This is a group of about 1,500 scientists worldwide who, together with their colleagues in the Virgo collaboration, have been at the forefront of the search for gravitational waves. We do a lot of outreach around the world. Traditionally, this has involved appearing in science festivals, visiting schools, attending special science events. All of that, of course, has had to change in recent months. So we are adapting and learning how we can carry out our outreach programs more effectively remotely. And in some ways, this is a great opportunity because it's letting us explore how we can reach communities and countries and parts of the world where we have not before been able to share our story. So that story is all about looking beyond the electromagnetic spectrum of light. We've been studying the universe for centuries using telescopes, for a long time just optical telescopes, but in the last century we've expanded our view of light to observe the universe all the way from gamma rays to radio waves. But what I'm going to share with you tonight is the story of how we have opened an entirely new window on the cosmos to explore the universe with gravitational waves, to use gravity as well as light as our window on the cosmos. So gravitational waves are a prediction of Albert Einstein's general relativity, which, as I said, we were celebrating a very special anniversary about last year. And well, a lot of my talk is going to be about Einstein, and Einstein has been connected to my career as a scientist for a very long time. The very first lecture course which I taught as a newly appointed member of faculty in Glasgow more than 20 years ago was Einstein's general relativity. This was quite challenging for a young lecturer to begin. But Einstein has always been a hero of mine. And I think from an educational point of view, partly the story that we try to tell is not just Einstein's scientific discoveries, but how he thought about science. And I think that for me is just as important as the wonderful aspects of physics and astronomy that he explored. It was his imagination, his great intuition, and his ability, to use the modern phrase, to think outside the box. So Einstein is, of course, a very famous figure in our culture, not just among scientists. And in fact, in 1999, Time magazine voted Albert Einstein the person of the 20th century. I should note, however, that this was the editorial board decision. There was also a public vote of Time readers, and the public vote was won by Elvis Presley. So you can decide for yourself who got that right. And in fact, Elvis will return to our story a little later as well. But Einstein's fame scientifically is largely to do with his general theory of relativity, his theory of gravity. So don't worry, I'm not here to give you a lesson in the details of all the mathematics. We just want to think about the key physical principle that underpins general relativity. It's that gravity is not a force between massive bodies, but a curving of space and time themselves. And we often use a rather imperfect, but I think still quite useful metaphor to describe that space-time curvature, which is to think of a massive body like the Earth or a star dropped onto a large sheet of rubber. And we would see the rubber sheet bend because of the mass of the object. And that bending, that curving of the rubber sheet means that particles, and indeed light itself, will no longer travel in a straight line. It will follow a curved path. Space-time tells matter and light how to move. And that curved path is in fact produced by the presence of matter in the universe. So matter tells space-time how to curve. This phrase captures the key underpinning ideas of general relativity. So gravitational waves within that framework are ripples in space-time curvature. Gravitational waves are what happens when the space-time curvature changes. And that means that we are looking for the effects of changes in the curvature produced when matter is moving around, when it's accelerating at very great speeds. In fact, technically, gravitational waves are produced when any matter accelerates. So even if I wave my fist, hopefully you can see that in your Zoom window, then I am producing gravitational waves. But because gravity is a weak interaction, then Einstein's theory showed that gravitational waves are incredibly faint. And in fact, to detect gravitational waves, well, frankly, Einstein was unsure if we would ever be able to do that. But even in the early years after he published his theory, it was clear that if we were ever to detect gravitational waves, we would need very massive bodies moving very, very fast. So a situation that does give us a chance to detect these gravitational waves is what's showing in this cartoon animation. We're giving the idea of two stars, in fact, in this case, two very dense and compact stars, which are orbiting around each other very close indeed. And that's the situation that we envisaged might allow us to detect these ripples in space-time. So how exactly would that be done? Well, it's a great challenge because the ripples in space-time produced even by two stars orbiting around each other, perhaps even colliding with each other, those ripples will spread out through the universe like ripples spreading on a pond. And by the time they reach us, those ripples, the disturbance in our patch of space-time, is going to be incredibly weak. In fact, we could calculate from Einstein's theory that the disturbance in our patch of space-time was equivalent roughly to about 1/1000th the size of a proton, the subatomic particle in the nucleus of an atom. Or maybe a better, more everyday way to think about it is to take one of the hairs on your head. I have rather a lot of those right now because I've not managed a a haircut since the lockdown began in the UK, and one of those hairs is about 10 to the minus 6 meters in thickness. And we are talking about a disturbance that's 1 millionth the width of one of those hairs. So, how on earth are we going to detect a signal so faint? Well, the operative word is on earth, because it's especially challenging to detect space-time curvature changes on the surface of the Earth, because the Earth itself is shaking, it's wobbling, it's causing disturbances that are nothing to do with colliding stars out there in the universe, but are just to do with the local environment here on Earth. So a big challenge to build a gravitational wave detector is to find somewhere quiet enough that those local disturbances do not drown out the signals we are searching for. And yet, remarkably, that is what we have done. And beginning first with the two LIGO detectors shown here in Livingston, Louisiana and Hanford, Washington, they are capable of detecting those tiny fluctuations on the scale of 1 millionth the width of a human hair. The way they do it is to use laser light. LIGO stands for Laser Interferometer. And the interferometry is to do with taking a laser beam and sending that light along two perpendicular directions. So that's what the animation in the corner of my screen is showing. And what happens is those laser beams are reflected from mirrors at the end of each arm. Now, the arms are long. In the case of LIGO, they're 4 kilometers long. And moreover, the laser light is circulated within the optics hundreds of times. So effectively, the arms are even longer. And then when the light is recombined and sent out to our diode detector, what we're looking for is changes in the interference pattern of that laser light. If the two beams travel exactly the same distance, then they will arrive in such a way that the two laser beams reinforce each other. It's what we call constructive interference. Now, in fact, LIGO is tuned so that when a gravitational wave is not passing by or there's no other disturbance, then actually the light beams do travel a slightly different distance so that they destructively interfere with each other. And that means there's no light at the output at all. But then along comes a gravitational wave. It stretches and squeezes the space-time within which the detector is sitting. A bit like this animation on the right-hand side. Of course, that's greatly exaggerated. But that stretching and squeezing changes the interference pattern of the laser light. And that means that what we see is a brightening as we get some constructive interference as the gravitational wave passes by. But again, to just keep in our focus how incredibly tiny this effect is, that 1 millionth the width of a human hair, measuring a displacement so small, is, in another way of thinking about it, equivalent to measuring roughly the width of a human hair, or maybe slightly larger, 10 to the minus 5 meters, on the distance between the Earth and the nearest star beyond the Sun, Alpha Centauri. So it's like knowing the distance to Alpha Centauri to the accuracy of the width of a human hair. So this is astounding technology, and I hold my hand up. I am not involved in the design and operation of LIGO. I'm a humble astrophysicist using the data to tell me about what's out there in the universe. And I am in awe and admiration for the scientists and engineers who designed and built these detectors. They are astounding, the most sensitive scientific instruments ever built. Now, the challenge is more than just having a sensitive detector, because we also have other sources of noise. Remember I said we can think of gravitational waves like sound waves, because the range of frequencies that LIGO is sensitive to are actually frequencies that our ears can hear. We'll say more about that in a moment. So the challenge we have is to detect a signal that's incredibly faint when there's a great deal of background noise. So anyone involved in education has probably had that experience of maybe the lunchroom in your school or college or university, where there's a huge amount of background noise and you're trying to interpret what the person even just in front of you is trying to say, with all of that background noise drowning them out. So that's the challenge we have. But basically, the noise is not equally bad at all frequencies. So for a ground-based detector like LIGO, there are many different sources of noise, and they're listed here, but I won't go into the details because we want to get on to talking about the astronomy. But all you need to take away from this rather complicated looking diagram is that at low frequencies of a few tens of hertz and high frequencies of a few hundreds to thousands of hertz, then the sensitivity of the gravitational wave detectors is rather poor. And that's denoted by this black curve rising at either end of the graph. But it's at its lowest at frequencies of a few hundred hertz. That's the kind of sweet spot in the middle where the sensitivity of LIGO is at its best. And that means it can detect strains, that's the stretching and squeezing of space-time, which are the most tiny. And again, the numbers are just astounding. We're talking, as I said, about 1 millionth the width of a hair on a scale of 4 kilometers. That corresponds to about 10 to the minus 22 in terms of the strain. But crucially, this can only be done within that narrow range of frequencies, because outside of that range, the noise is just too great. And up until 2010, the noise was too great even in that middle range because nothing had been detected yet. But we were confident that the signals were out there, we just needed to make the detector quieter. And that was what happened when LIGO was upgraded to advanced LIGO. So there were certain bits of technology that were changed and improved and upgraded to make the detector more sensitive, effectively by making its local environment quieter. So I'm just going to highlight one of those, which my institute in Glasgow played a leading role in. In fact, the UK played a leading role in, and that was increasing the sensitivity at low frequencies by improving the suspension of the mirrors at the ends of the arms. So a complicated suspension system was created, replacing the steel wires that had been used up to that point prior to 2010 by glass fibers, silica fibers, incredibly delicate, but also really rather strong, and crucially not so susceptible to wobbling due to those low frequency fluctuations. So that meant the detector was quieter and more able to listen out for those signals coming from the universe itself. So we began operation in advanced LIGO mode in September 2015, and within just a few days, the detectors had recorded their first signal. Now, at the time, of course, we were not sure that this was indeed a gravitational wave signal, so we didn't publish the results until February 2016. Maybe you recall when that happened, it was widely around the world. And what you see here is a visual representation of that signal, referred to as a cherp, because you see the rapidly increasing frequency as essentially the two objects are spiraling around each other and colliding, and that's when the frequency reaches its maximum, space-time wobbles up to lower, and then things settle down. So this pattern, this cherp pattern, was seen when LIGO had first and LIGO fixed it. And bearing in
Martin,
mind,
we don't hear you well. It's probably the sound.
Martin, the gravity waves are too noisy. Martin, can you turn down the gravity waves?
Well, we did need to be really sure of that. So that's why it took many months of painstaking analysis to confirm that yes, we regarded this as our first ever detection of gravitational waves. So what did that signal come from? Well, you probably know this story too. We deduced that the signal had come from the collision of two black holes. And I'm reminded of Andy Newsom's talk where he said that everyone is interested in black holes. And sure enough, when we did announce our discovery, the global coverage was remarkable. We were on the front page of hundreds of newspapers the following day. And as Rosa very kindly mentioned, 3 of our senior members of the collaboration were awarded the Nobel Prize for Physics in 2017. So the nature of the signal allows us to determine the properties of the sources that produce it. So it's that chirp pattern, and in particular, the way in which the frequency changes and the amplitude changes, that allows us to deduce that we are talking about not just any old stars, but 2 black holes spiraling in around each other, colliding, merging, and then space-time wobbles some more. We have what's called the ring down, and then we have a single black hole just sitting there, and the universe goes back to normal. So by analysing the data, we could deduce that these 2 objects were spiraling around each other at more than half the speed of light just before they collided, and that their separation was only a few hundred kilometres, or a few times what we call the Schwarzschild radius of a black hole with the mass that we had deduced from the pattern in the signal. And all of that really convinced us that these objects had to be not just black holes, but very far away. In fact, as George Lucas might put it, we had detected this signal coming from a galaxy far, far away. And indeed it had happened, as the films say, a long time ago. The signal had been traveling towards us for more than 1 billion years before our LIGO detectors picked it up. So here's an animation informed by the data themselves, giving a flavour of what was going on as those black holes orbited each other. So we were able to deduce that one of them had a mass of 36 times the mass of the Sun, while the other had a mass of 29 times the mass of the Sun. And when they merged, there was this burst of gravitational wave energy. Let's just play it one more time so you get a chance to see that. They spiral in, they go faster and faster, the waveform evolves, and then as they merge, we get this sudden burst of gravitational wave energy represented by the red spike. That's just so we can visualize it in color. But the gravitational waves would not give off any light at all. We are not talking about light waves, we're talking about a different form of radiation altogether. And when those black holes merged, they settled down into a single black hole with a mass of 62 times the mass of the Sun, with a little uncertainty, but the most likely value was 62. So 29 and 36 make 65. 62 solar masses was the final black hole mass. That tells us that in just a fraction of a second, the equivalent of 3 times the mass of the Sun had been converted into gravitational wave energy. And remember, we don't expect that any light whatsoever is given off when such a collision occurs. So in a very real sense, we're probing the dark side of the universe. And I think it was Darth Vader himself who once said that you should never underestimate the power of the dark side. And we can see that for ourselves if we think about that 3 times the mass of the Sun converted into energy in only a fraction of a second. It corresponds to more than 50 times the luminous power, the light power, of every star and every galaxy in the entire universe. And yet no light was given off whatsoever. It's because all of that energy is locked up in space-time itself and is then released when the black holes collide. So we only had the 2 LIGO detectors operating at that time. But on August 1st, 2017, at the start of our second observing run, the event I just described, the first detection, was the highlight of the first observing run. But then 3 years ago, the second run began. And with Virgo now upgraded as well, Virgo is in Italy, close to Pisa, that gives us a much better way to determine the sky position of where the gravitational waves are coming from. Think of it like triangulating your position. So each pair of detectors defines a ring on the sky where every source on that ring would give the same delay in time between the signal arriving at one detector and arriving at the other. So if you've only got 2 detectors, you don't really know where the signal came from on that ring. But with 3, that gives you 3 separate rings, and where the rings intercept, well, that's where your signal came from. So within just 2 weeks of Virgo beginning to take data, we had detected a binary black hole merger, another one, and this time much better localized on the sky. So this map gives a sense of that. These larger regions, including the very first detection that we talked about before, they typically would cover hundreds of square degrees on the sky, or even 1,000 square degrees or so. Whereas this new event 3 years ago was localized to about 60 square degrees. That's about maybe 250 times the area of the full moon on the sky. And that was August 14th, 1 week before the solar eclipse, remember, but just a few days later, an even more remarkable event would occur. We'll get to that in a moment. But just before we do, let me fast forward a little to 2018. And in December 2018, by that time, we'd observed a total of 10 binary black hole collisions, and that gave us a catalogue. Astronomers love to build catalogues. It's how we learn not just about individual events, but about the population, and what that tells us, for example, about how sources are formed and maybe how they might evolve. So our catalogue was giving us the first hints about that for binary black holes. And many of the lessons we learned were really very exciting. We were discovering black holes that were more massive than we had previously thought would be typically formed from the collapse of stars, from supernova explosions. So lots to learn, but even with only 10 events, of course, the picture is not very complete. But we could, for example, start to rigorously test general relativity. Now, this is a very complicated slide, so don't worry about the details. Let me just home in on 2 aspects. One is on the left-hand side, and this complicated diagram, all you really need to know is that if general relativity is correct, then the data should be homing in on 0, 0, the middle of the graph. And they do seem to cluster around that point. And then on the right-hand plot, all that's really important here is that if general relativity is correct, then all of these numbers plotted in the graph should be rather small. And sure enough, they are. So all of this means that from our catalogue, we were starting to put real constraints on general relativity. And the bottom line is, Einstein was pretty pleased because general relativity seemed to be passing the test so far. But we've got to keep testing the theory with more and more data. So let's go back now to that August 17th date 3 years ago. Because during August 17th, LIGO and Virgo detected another event. I'll play this again because I was talking over it. There might even be a short time lag in the PowerPoint. So let's play it and I'll keep quiet this time. So hopefully what you heard there was the rising chirp sound of a gravitational wave signal that's shown in the bottom. And it's rather different from the black hole signals because it lasted much longer. And that tells us that the compact objects colliding were much less massive. In fact, we could tell almost immediately that this was very probably a collision of 2 neutron stars, so not black holes. And unlike black hole collisions, when neutron stars collide, we do expect to see some light, in particular, to see a gamma ray burst. And that was seen by NASA's Fermi satellite and ESA's Integral satellite to occur about 1.7 seconds after the binary neutron stars merged and the gravitational wave signal peaked. So what was emerging then was a remarkable story. What we talk about as a new dawn for multi-messenger astronomy, observing the universe not just in light, but in gravity as well. Because the coincidence in the sky position of the gamma ray burst and the gravitational wave source, in fact, was really rather precise. There were only a few dozen galaxies in that patch of sky. And that was aided by the Virgo detector now being in operation. So it was relatively straightforward for optical telescopes to identify in which galaxy something had gone bump in the night. And in particular, it was this galaxy here, NGC 4993. This image was taken in April of that year, this one on August 17th, and this new star has appeared. And then the similarity in the arrival time of the gravitational waves and the gamma rays, only 1.7 seconds apart. Well, they'd been traveling for about 40 megaparsecs. So that's in terms of light years, about 130 million light years. So that meant that even if they set off at the same time, then the light had only lagged behind by 1.7 seconds. In fact, we think that gravitational waves and light travel at exactly the same speed, and the time delay was because the gamma rays were emitted ever so slightly later than the gravitational waves. But even if we didn't assume that, this was telling us that the speed of gravity and the speed of light have to be incredibly close to each other. And that's what's shown in this little equation in the bottom left corner. I know equations won't be to everyone's taste on a Saturday evening, but you can see the numbers are incredibly small. So according to GR, gravitational waves travel at exactly the speed of light. And again, GR seems to pass the test. But the remarkable signs to come from this new aftermath star, what we call a kilonova, produced in the aftermath of the gamma ray burst, which in turn was preceded by the neutron star collision, all of that was pointing towards an idea which theoretically had been predicted, and now we had good evidence for it, that kilonovae are good places to make the heavy precious elements like gold and silver and platinum. So the gold in my wedding ring, for example, almost certainly came from the collision of two neutron stars. Not this one, but another collision that may have happened much longer ago. And then the other bit of remarkable science that came out of this first multi-messenger event, gravity and light, was that we could, for the first time, use gravitational waves to try to measure the expansion rate of the universe in a completely different way. So we get the distance from the gravitational waves, the identification of the host galaxy told us its redshift, and the Hubble-Lemaitre law predicts that there's a relationship between those two due to the expansion of the universe. Now the problem is, in recent years, our attempts to measure that expansion rate, what we call the Hubble Constant, H0, have been rather perplexing. There's been a range of methods that come up with very different answers. Now, they're not so different, you might think, but with the quoted uncertainties, there's a group of methods that give smaller values, shown by this green vertical band, and another group of methods that give the higher values, shown by the orange band. And we simply don't know why they don't agree with each other. So the gravitational wave method could hopefully resolve that tension. Now, not with just one single event, because the uncertainties in our measurement are so large that we actually span all of those values, the green band and the orange. But this will improve in time. As we observe more and more sources in the future, the situation will get better. Now, I'd better march on. What I want to do now is say a few words about what's been happening since 2017. And then if time allows, I'll briefly talk about the future as well. So our third observing run began in April 1st, 2019, and it was suspended on March 27th due to the COVID pandemic. But what we were seeking to do in this third run was to make our detectors even more sensitive, to make further improvements to the detectors so that they could detect signals from deeper into the universe, and hence we would expect to observe more such signals. And sure enough, that's exactly what happened. So this plot shows the increase in the rate of detecting events throughout that third observing run. The first part ran to autumn of last year, and then we resumed again in November and ran through to March, as I said. So this event rate appears to have risen, but there's a minor caveat here, because so far what we were publishing was candidate events. We wanted to do that very quickly so that astronomers could use telescopes in light to go look for a counterpart in light. So one of the ways we get the information out there is using this app. And again, you can download that for yourself. You can get it from our LIGO website or from Google Play or the App Store. Now, we're not operating right now, so you won't get any alerts now. But when we come back online, hopefully in 2021, then again, this will wake you up when there's a candidate gravitational wave event. But there are 3 of those candidates, the 50 or more candidates, that we've already confirmed to be definite detections. So that means we've done the hard work to analyze the data super carefully over many months to confirm that it's the real deal. So the first of those we announced in January of this year, and the event itself was detected in April of last year. And this was another collision of neutron stars. But this time we didn't see a kilonova and we didn't see a gamma ray burst. And there's many possible reasons for that. It wasn't so well located on the sky, so it was hard to know where to point the optical telescopes. And it was also several times further away, and hence any light emitted would have been fainter. But it was still a very interesting event because the combined mass of these 2 neutron stars that we worked out from the gravitational waves, well, this graph here shows that it was up in this kind of region, about 3 and a bit times the mass of the sun. And that's more massive than pairs of neutron stars that we've detected using radio waves or using X-rays or gamma rays within our own galaxy. So does that mean that we're probing a different population? Well, maybe, but sometimes we need more such detections before we can build up that picture. But it's very intriguing that the LIGO Virgo detections are more massive than the neutron star pairs that we see in our galaxy. And then in April of this year, we reported another binary black hole merger. And this was a system where the signal was detected in April of 2019, the 12th of April to be precise. And this was a pair of black holes where the masses were not so equal. Most of the others up until then had been more or less exactly the same mass, the 2 black holes. Some more massive than others, but more or less evenly split in the binary pair. But this one, the smaller black hole, was nearly 4 times less massive than the larger one. And that's interesting because it gives us a different kind of gravitational wave pattern. It gives us what are called higher multipoles, or to use the sound analogy again, think of them like higher harmonics. So if you think of the main gravitational wave signal that you get when the masses are equal as middle C, let's say, then the next harmonic would be a perfect 5th up from that, G on the C scale. And curiously enough, there's an Elvis song that begins with a perfect 5th, I Can't Help Falling in Love with You. And that's kind of how the media reported this detection. They said that the LIGO and Virgo detectors had been hearing the harmony of black holes in the universe. They'd been hearing Elvis. So as I said, Elvis comes back in to our story again. There are very interesting bits of science that we can get from using these higher multipoles. It allows us to work out the distances rather better. That's what this strange boomerang shape is showing in this figure from our paper, because the boomerang is rather larger because you don't know the distance all that well, because you've also got to measure the angle of how the 2 black holes are tilted towards us. But measuring the higher multipoles, the higher harmonics, if you like, helps us to work that out. So I'm nearly done, almost out of time. There's one more detection that we've announced so far, and that is a detection where we have a very massive star and we have an even less massive companion. So the ratio in 1904-12 was nearly 4 to 1. In the case of 1908-14, the ratio was more like 10 to 1. And curiously, the less massive companion was in a kind of range where we're simply not sure if it's the least massive black hole we've ever found or the most massive neutron star. So that's what this rather strange looking graphic is conveying. It's conveying the great uncertainty we have about the nature of the companion star. So as we all know, astronomy sometimes gives us more questions than answers. and that's very much the case with this event. Either way, it's in what we term the mass gap, the gap that appears to exist between the heaviest neutron stars and the lightest black holes. So maybe it's a new type of object altogether, but probably it's just that that mass gap isn't really a gap at all. It's just that observing in light hasn't allowed us to probe the objects that sit in that gap. But now with gravitational waves, we can detect them, and hopefully in the future, we'll detect many more. So that's kind of where we are. And this is the graph I showed before. Remember that the O3 events, a total of 67 across O1 and O2 and O3. Now, 11 of those were in O1 and O2. They're published already. The other 56 are candidate events, 3 of which we've already published and confirmed. But in the coming weeks, we're going to announce some more. So I can't share the details of those with you yet, but I can promise that in a very short time, we'll have lots more to tell you about what we've detected so far. So it's a case of watch this space, or maybe it should be watch this space-time. And just to really give you 2 more minutes of the future, and then I really should stop, what I just want to mention is what comes after that. So we've got our 3rd observing run completed, still doing the analysis. Our 4th observing run is coming up, we hope, towards the end of 2021, if it's not delayed too much by the pandemic and all the great uncertainty that there is right now. But if you look at the improvement we got when Virgo came online, because we could localize in the sky so much better, well, it would be great if we could do that even more with additional detectors. And that's just what's going to happen, because Kagra is a detector in Japan, and it's basically about good to go. It, in fact, started taking some data in March, but it will be ready, we expect, to join our 4th observing run in about a year or so's time, and that will improve things. And then a little bit later, there's going to be another LIGO detector, this time in India. So LIGO India promises to come online in about 5 years' time. And with the big 5, that will allow us to localize sources in the sky so much better that will greatly improve our prospects for determining where the gravitational waves came from. Now, I'm just going to skip a few slides because I have taken more time than I planned, but I just want to leave you with some resources. I can go back to those intervening slides if there's time and they're relevant for questions. I think they might be. I'm anticipating the questions I may get. But let me just emphasize that a lot of our educational resources are freely available to use. You can find a lot of material on LIGO.org. For example, science summaries of our science papers, but written for a non-specialist audience. Lots of multimedia, our LIGO magazine. And here's just highlighting some of the resources we have. There's also a dedicated section for educational resources, so take a look at that. And in addition to the summaries describing the detections, we also wrote one about a year ago which describes our methods of analysing the data. Now, I can't pretend that those are straightforward, at least for, say, high school level, but we are working on some tools that might well be appropriate for high school that simplify things a little. And certainly for undergraduate students or college students, then I think our data analysis should be within their grasp, and we've tried to make that easier by putting a lot of data on our Open Science Centre. So our Open Science Centre, you can find the data for all of our published detections, but most importantly, you can also find tutorials and software tools. So the programming language of choice is Python, and the tutorials exist in the form of a series of YouTube-style videos that guide you through the use of Python notebooks to analyze the data for yourself. So you're more than welcome to play around with our LIGO Virgo data, and there'll be lots more data published there in the coming months. Now, of course, if you want to be more of a passive participant in the subject and not get your hands dirty with coding, you can still keep abreast of the latest developments by following us on social media, or you can check out our YouTube channel. There's a lot of good material there. And of course, you can download the cherp app. So nothing will come through on cherp right now, but once the detectors are up and running again, then who knows, almost every day you'll be getting candidate events straight to your cell phone. So I hope you've enjoyed this journey through gravitational wave astronomy. When we made that first neutron star detection just over 3 years ago, well, we came up with the idea of an in-spiral toast where the glasses spiraling towards each other. So, you know, I hope you might raise a glass with me to the bright future of gravitational wave astronomy a bit later this evening. And I'm absolutely delighted to be part of this event, and I'll happily answer now any questions that people may have. Thank you very much.
Martin, amazing as always. It's just, as you say, we come here to learn a bit about gravitational waves, and we go back like, what is this? Is this true? So yeah, there's more questions now than answers in our minds. And hopes
of course, I'll happily answer them on the chat window if we run out of time. So
we do have time. Yeah, we do have time for a few questions. Yeah, we do have time. So one of the questions is from Robert Baker. He's asking, why aren't radio waves used in the arms?
Okay, so we need the precision that you get with laser light. So one of the features of a laser that makes them very useful for this is that we know their wavelength very, very precisely. But in fact, radio waves are used as a form of gravitational wave detector. And I'm sorry I didn't have time to talk about that. It was among the slides that I skipped, but I won't waste time going back to them. But my presentation will be available, I'm sure, afterwards. And what you want to look for is where it says pulsar timing. So we can look for gravitational waves passing through our galaxy and disturbing the radio waves that come from distant pulsars, rapidly spinning neutron stars. And if we look at a network of pulsars in our galaxy, we can triangulate where the gravitational waves came from. So that pulsar timing method hasn't detected any signals yet, but we're confident it will in the future. And that will be a great addition to the ground-based detectors that have made some discoveries already.
There's another question by Jacob Brown. On the noise graph, I see 3 sharp spikes that I have to deal with suspension thermal noise. What are those spikes associated with?
Again, I won't go all the way back, so it could be that I'm not referring to exactly the same spike, but the general pattern is where you see a spike, it's because of a resonance. So the resonance will occur if there's a natural frequency within the material of the mirror, or the fiber, in fact, which tends to wobble. And it means if you're trying to detect a signal at that frequency, then you're not going to do it because the wobbling drowns it out. So one of the reasons that the advanced detectors were so much better is that they had multi-stages. So the mirrors were suspended to the next stage, and then that stage was suspended to a stage above. In total 4. So here's something you can try for yourself. If you have 2 or 3 or even 4 yo-yos and you tie them together, what you can see is that if you shake the one at the very top, then the yo-yos joined by, it will need to be a short piece of string, further down, they don't shake so much. They're more isolated from the one at the top. You can't isolate completely, so that's why you get the spike. But because those spikes are so narrow, it means that the effect of the resonance at least doesn't pollute other frequencies very much. So that really has been the goal in designing the detectors, is to accept that they cannot be perfect. But if you localize the disturbance to be really narrow in the resonance, then the rest of the frequency range is much more sensitive.
Another question by Hamal Mimoni is Devious Arguments. You certainly have heard about the suspicions, especially from the very popular blogger Sabine H., that ultimately we don't have independent proof of the astrophysical origin of these gravitational waves, recalling that the strong proof from gravitational wave found in summer 2017 was problematic because it is not a prediction as it was found after the gamma ray burst detection. Nothing wrong and absolutely but troubling. Is the gravitational wave relation to astrophysical mergers so watertight. The evolving understanding of the various mass caps may be understood as doing adjustments. Please don't take it negatively, but just see it as a chance to shield your case.
I don't take it negatively at all, but I think since there are probably other questions to answer, and since there is very little time left, I'm not going to dignify the arguments of Sabine and the others with a lengthy reply. I mean, you know, she's asking interesting questions, but in my judgment, they have been fully answered by the collaboration already. And therefore, what I'd like to do is to recommend that the person asking the question read our paper on a guide to gravitational wave data analysis. If the person asking the question still has some issues with our data analysis methods, then I'll happily discuss them. But as far as I'm concerned, if you haven't read the papers, then you're not fully aware of the counter arguments that we have already made to all of those disputes.
There's a question here from Aziz Kaihan. It has been mentioned that gravitational waves might be the key to prove whether or not multiverse theory is correct by observing gravitational waves from the Big Bang caused by the end of inflation. How do you see that likely to happen? And if it is likely, how different would them be from other gravitational waves?
Oh, that's a great question. I mean, the previous one was a great question too. I just didn't have the time to unpack it in the level required. And sadly, I don't really have time to do that here either. But let me just mention again a few things that you can go look at. So the crucial point here is that if gravitational waves are produced in the very early universe, then they are indeed regarded as a strong indication that inflation occurred. And if inflation occurred, then it's very natural in inflationary theories for there to be a multiverse. Now, that's not the same as saying that there's definitely a multiverse. It's just saying that the observations would be consistent with some aspects of multiverse theory. So I think it's an absolutely fascinating area, but I think it would be unwise for us to expect that even if we do detect gravitational waves from the very early universe, that this in some sense proves that there's a multiverse. But it would certainly give us much more information than we currently have to try to answer such a question. The crucial thing is, though, is can LIGO and Virgo detect such a signal? And to be honest, it's going to be extremely tough. A much better way to detect gravitational waves from the very early universe is to use the cosmic background radiation and to look for the imprint that the gravitational waves would leave on the polarization of the cosmic background. So the steps in the chain are observe that polarization with the CMBR and then interpret that as a strong indication of inflation, and then interpret that as supportive corroboration that maybe there's a multiverse. I don't think that's proof, but it would be really fascinating if we could do it.
Very interesting, very, very interesting. There is one that is most voted from Nuno Miguel Betancourt. Would it be interesting in the future to build a huge interferometer in space, attached to a space station, for example?
Yeah, I wonder if you would let me just, I know we're almost out of time, but if I can just share my screen again.
You still have 6 minutes.
Ah, perfect. Because I did feel bad about skipping one of the slides, and in fact, if I just go back to it, it will help provide a short, but I hope complete answer to that question. So the questioner was asking about, so am I sharing? Let's see.
Not yet.
Not yet, but I will be in a moment. That is puzzling. I don't know why. Right. Right, okay, I'm sharing my screen, and can you see a diagram that says gravitational wave astronomy at the top?
Yes.
Good, okay. So the question is about building a spaceborne detector. And just before I answer that, very briefly, let me again mention the pulsar timing. That was in relation to the very first question. So that's using radio waves on the scale of our galaxy as a galactic scale detector. So that's good for very, very low frequency gravitational waves. And then LIGO is sensitive, as Virgo is as well, to higher frequency gravitational waves. But in between, there's a range of frequencies where the ground shakes too much. So building a detector on the ground would be no good. But if you could put a detector in space, then you would be sensitive. And there's going to be one. And the European Space Agency is leading a mission called LISA, which is scheduled to fly around 2034, working with NASA. And it's going to be 3 spacecraft, millions of kilometers apart, sending laser beams back and forth. So the principle is roughly the same as LIGO, but because it can detect much lower frequency gravitational waves, it will be sensitive to supermassive black hole binaries colliding in the cores of galaxies. So again, watch this space, it's all coming our way. And in fact, LISA, you know, will be an even more exciting mission in some respects, because it will probe very, very deep into the universe, much deeper than LIGO and Virgo can.
So again, very exciting times, and maybe I'm not wrong to say that maybe the students who are going to work with this mission and make most of the outstanding discoveries are in school right now, or secondary school,
exactly.
maybe entering university. Yeah?
Exactly. I thought Bernard made that point so eloquently in his talk about going to Mars, and it's the same with LISA. We need to organize. I'm in a leadership position in LISA, which is a great privilege right now, but I realize that I will be basically retired when LISA flies. So we need those students to be the ones that carry it forward in the 2030s and beyond.
Well, one more question is from Azim Khan, and he's asking, how do we select the location for setting up LIGO? Could you explain what are the most important features?
Absolutely, that's a really great question. Again, I'll be brief, but let me just mention that the new one in LIGO India, a great deal of effort was taken to choose a site carefully. And there are political factors, there are geographical factors, and there are astronomical factors. To be honest, the political ones are probably the most important, because you need a government, a country, or several countries to decide that they're going to do it. They need to build the roads and the infrastructure, and maybe they have some reason why some area is better than others. But there are other factors too. It would not be a good idea to build a detector where the ground shakes too much, where there is a lot of seismic activity. You might argue that that's maybe not a good reason for Kagra in Japan being where it was. So the astronomy factors are almost the least important in a way, but nonetheless, if you've got your sites as far apart as possible, then that will mean that you can pinpoint on the sky the best possible positions. So actually, the best place of all is probably Australia. And there were some plans to build a detector in Australia about 10 years ago. We hope that our Australian colleagues will be able to build one there in the future. So maybe that will be the 2030s. It might be a long time, we wait, but that would be wonderful, because Australia, as we know, is very far from the other continents.
Amazing. So yeah, unfortunately, we do not have time for more questions. Martin, there is 2 questions. Maybe you can type the answer for the people who have asked them.
Sure.
Thank you so much for the presentation, the amazing presentation as usual, and for bringing us such a cutting-edge topic on research and keeping us up to date on what's going on. Thank you so much.